Oh, look here. Look what we have. We have run into parts of memory. This is kind of gives you an idea of what hackers do if they know what they're doing.
Only one thing. You forgot the...
Bruh.
If you forget something in assembly, not trying to teach assembly, trying to give an appreciation for what really happens behind the scenes when programming in higher level languages, hopefully to be a better software engineer.
I only got 9 hours of sleep last night.
9? I only got 7. 7? I only get 4.
You guys are getting sleep?
Assembly, a low-level programming language designed to simplify the instructions fed into a computer's CPU. In other words, it's a human-readable abstraction on top of machine code, so programmers don't have to manually count ones and zeros. The first assembly language was created by Kathleen Booth in 1947 for the all-purpose electronic computer. Over the next decade, it evolved into many different formats to power the supercomputers of the day, like the IBM 7090, which had a $20 million price tag in today's dollars. Writing code in assembly was standard until the emergence of high-level languages like Fortran a few years later. However, assembly is still used today for direct access to the bare metal hardware and to address low-level performance issues, often on device drivers and embedded systems, and it's also used to run native software in a web browser via WebAssembly.
Note, remember WebAssembly.
What's tricky is that each assembly language only works on a specific CPU architecture, like ARM for Apple Silicon and Raspberry Pi, or x86 for Intel chips. To get started, you'll first need an assembler, like the NetWide assembler for x86 chips. An assembly program is divided into 3 sections. The text section contains the actual logic for the program. By convention, it contains an entry point called start, which is where the code will start executing. The data section is where we can initialize constants, or data that does not change. To declare a constant like a string, we start with a label, then use db for defined byte to place the hello world string into memory. By itself, it doesn't do anything, and to print it to the standard output, we will also need its length. We can use equate to convert a symbol into a constant. The $sign will subtract the current position from the hello label, providing the length of the string. And now these constants can be referenced from the start label. In the main program, each line of code contains an instruction along with one or more operands, and there are hundreds of instructions built into the language. Now, to perform operations quickly, the CPU has a limited number of registers, which are like 64-bit chunks of memory built directly into the CPU instead of the RAM. We can insert data into a register with the move instruction by providing operands for the register name and the data to store there. In this case, number 1 is used because it corresponds to system write on Linux. Next, we need to tell the system where to write, in which case we'll move 1 into the RDI register, which corresponds to the standard output in the terminal. The next register stores the message to write along with its length. Now execute the code stored in the CPU by calling the operating system kernel. Almost done, but we'll get a segmentation fault if we try to run it at this point. Update the RAX register with 60 for system exit and provide an error code of 0 for success. Now use the assembler to compile or assemble your code into an object file, then use the linker to convert it into the final executable.
If you remember what we did with Lua, and I just picked one of the higher level languages that we've done, we were able to print hello in a loop. So let's concentrate on this part of the program. We somehow want to put printing hello in a loop. Now, if we take a look at Lua, notice that we have some sort of a counter, a place in memory or in a register of a CPU, right? That we initialize to 0. And then implicitly here, although it's not obvious, we're doing a compare, and then we're incrementing. So we start at 0, we print, we compare and test, and we increment. All that is being hidden from you. Here it is in assembly. This is our I right here. We're going to start the counter at 0. We have a label. Why do we have a label? This is the start of the loop. That's just a label. All right, that's to tell the assembler, our building process, that this is where we're going to come back to. We increment our counter, our I. We compare. Is it 5 yet? No, it's not. So jump if not equal, JNE, to loop start right there. So we'll take that, copy it, paste it here, run it, and there it is. I want to show you a different version to kind of just give you a teeny little idea of how or why assembly programmers can be really anal, and they actually count instructions, the number of instructions, because some of the devices that are being programmed are tiny little things. It's not just a computer. So notice right here that we have 3 instructions. We have the inc, the increment, the compare, and jump if not equal. If we go and do a decrement instead of an increment, this time I have our original code without the loop on the right, sorry about that, and the loop is on the left. But this one is a decrement. we start at 5 instead of at 0, and we're going to count down. What does that buy us? Look, there's no compare here because the jump instruction is the compare. It's the compare and the jump all at one time. So we start at 5, we print, we decrement our counter, jump if not equals 0. Okay, I'm going to finish off with trying to force a mistake in assembly. All right. So we already know we have the loop. We know we have the 5 letters of hello plus a new line, right? Which makes 6. But let's say I made a mistake and I said, oh no, it's only 5. So that means the new line doesn't get printed. We run it and they all get run in a row. Okay. But what if I went the other way? What if I did 7? Oh, we got this little issue. Okay. Is that a huge deal? I don't know. What if we did 70? Okay. What if we did 700? And it still hasn't caused us any problems. What if we did 70,000? Oh, okay. You know what? The website has protections. Let's do 5. No, okay. 1. It will do, it will allow us. Oh, look here. Look what we have. Let me scroll look. We have run into parts of memory that hold the file name and our loop. This is part of our actual, if this was a file that we had created, look at this. You see this? So this is an idea of what can happen if you make a mistake, but not only that, this is kind of gives you an idea of what hackers do if they know what they're doing.